Hey guys, this is CHEMPLIFIED and today we will talk about a simple but an important topic of chemistry, hybridization. So let's start. Before we reach hybridization or the definition of hybridization, we need to know what was the need of hybridization. Why we are studying hybridization. Now, hybridization was introduced after valence bond theory because there were a few limitations, and to tackle those limitations, hybridization was introduced. Now, what were those limitations? Consider the molecule CH4. It is a methane molecule, and you know that it is known practically that all the bond length of carbon and hydrogen are of equal length. All these four bonds are of equal length. Now, how this bond formation takes place according to valence bond theory? According to valence bond theory, how this bond formation take place? Let's take a look. in in ground state of carbon, this is the ground state of carbon. uh, 2s orbital have 2 electrons and p orbital have 2 electrons. Now in excited state of carbon, the one electron from 2s orbital will jump to the one orbital of 2p. Now we have four different orbitals having single electron. Now according to valence bond theory, each each of the four hydrogens will make bond with these four orbitals, of carbon. There is one orbital from 2s orbital and three orbital from 2p, that is 2px, 2py and 2pz. You all are familiar with that. Now if you make this bond between carbon and hydrogen, this will be one bond and these three will be bonds between carbon and hydrogen. Now if you look closely, this is the bond formed by the overlap of 2s orbital and 1s orbital of hydrogen, right? And now look at these three. All these three bonds are formed by the overlap of 1s orbital of hydrogen and 2p orbital of carbon. Now this particular bond should be different from these three bonds. Why? Because the overlapping is taking place between 2s orbital and 1s orbital, and in this particular case the overlapping is taking between 2px, 2py, 2pz orbital and 1s orbital of hydrogen, right? Now according to valence bond theory, if this particular kind of bond formation takes place, then that means that there must be two types of bond in methane molecule. One of type 2s and 1s, and other is 2p1s, 2p1s, 2p1s. So three bonds should be of equal length, and one bond, that is the bond between 2s or bond between the orbital of 2s orbital of carbon and 1s orbital of hydrogen should be of different length, right? But in reality this is not possible. All the hydrogen bonds of carbon, all the bonds of carbon and hydrogen in methane are of equal length. So how is this possible? So this was not explained by valence bond theory. So to explain this particular concept, we introduce the term hybridization. This is the structure of methane, and according to valence bond theory, one particular hydrogen should be of different length than the other three. These three shown in blue are of equal length, and this one in particular should be of different length, right? But this is not true. In reality, all the four bonds of carbon are equal. Now that's where hybridization came into play. Now let's go with the definition. Hybridization is defined as the mixing of atomic orbitals belonging to the same atom but having slightly different energies, resulting in the formation of new orbitals of equal energies and identical shape. The new orbitals thus formed are known as hybrid orbitals. This is the definition. You can learn it Now there are a few terms that you should know about. First of all, we will talk about slightly different energies. What is the meaning of slightly different energies? Let me move it a little bit. We know that the order of energy of orbital is 1s, 2s, 2p, 3s, 3p, 4s, 3d. This is the energy of orbitals. That's how this is the increasing order of energy of orbitals. Now, of equivalent energy or slightly different energy means that the hybridization or the intermixing can only take place between slightly different energy orbitals, only between those orbitals that have slightly different energies, like 2s 2p, 2p 3s, 3s 3p. But the hybridization will not take place between the orbitals having large energy difference like 3d and 2s. Now how will you get the energy? There you have to apply n plus l rule. We will talk about it while when we study principal quantum number, azimuthal quantum number. Then we will talk about this. N means principal quantum number, L means azimuthal quantum number, right? So just remember that the energies of orbitals, two different orbitals, should be equivalent or slightly different. Then only they will intermix with each other to give a new set of orbitals that have equal energy and identical shape. The new orbital thus formed are known as hybrid orbital. This is the definition. Just remember that for intermixing, the orbital should be of close energy, not far away from each other, right? So this is the definition of hybridization. Now let's move to the next. Now we will talk about types of hybridization. Types of hybridization. We will first talk about sp hybridization or sp hybrid orbital. For that, let us consider an example BeF2. Now the ground state of beryllium is this: 1s orbital contains 2 electron, 2s orbital contains 2 electron. Excited state, in excited state, 1 electron will jump to the p orbital. Now in hybridization, what happens is the 2s and 2px orbital will intermix with each other, to form a new set of orbital called sp hybrid orbital. Now why it is sp? Because the intermixing is taking place between one s orbital and one p orbital. How many p orbitals are there? There are 3 p orbitals, out of which only one is taking part in hybridization. So the hybrid orbital so formed is sp hybrid orbital, right? Now let's take a look at the structure. Now this will be the shape. The center is the beryllium atom. Now this is sp hybrid orbital, and the two fluorine atoms will attack from the two side and form bond with the Be atom. That's how the bond formation will take place in beryllium, right? This will be the structure. The angle is 180 degree. This is the shape of sp hybrid orbital. The intermixing take place between 2s orbital and 2p orbital. You can take a look in any book and you will find all the shapes of different orbitals which we will talk about later. The first one is sp. So that's how the bond formation take place in BeF2, right? Now let's talk about sp2 hybridization or sp2 hybrid orbital. Example is BF3. The ground state of boron is 1s2, 2s2, 2p1, right? Now in excited state, what happens is one electron will jump to the p orbital. Now what happens is, now this will not take part in hybridization because of two reasons. First, the energy is different, not 1s and 2s. The energy is different for 1s and 2p. There is large energy difference. And the second reason is 1s orbital is very close to the nucleus. So the force of attraction between 1s orbital electrons and the nucleus is high, and nucleus won't allow it to participate in any bond formation, right? So what happens is the mixing of orbital takes place between one s orbital and two p orbitals. So this time the hybrid orbital will be known as sp2, because one s orbital is participating and two p orbital are participating. Those two p orbitals are px and py. In my case, it can be pz also, because all these three orbitals are degenerate. They have equal energy. All the three p orbitals have equal energy and any two can participate, right? So this is sp2 hybrid orbital. Now let's look at the structure. This is the shape of sp2 hybrid orbital, and the central atom is boron. The structure will be like this: bf3. The angle between the two bonds is 120 degree. This is just sp2 hybrid orbital of boron. This whole is sp2 hybrid orbital of boron. The fluorine will attack not from s orbital. The fluorine will be using its p orbital, and the bond formation will take place. So that's how the bond formation take place in bf3 according to hybridization concept, right? Now let's take a look at the next. sp3 hybridization. Most commonly used hybridizations are sp3 and sp2 hybridization in organic chemistry. Now here in this case we are taking the example of CH4, methane. The ground state of carbon is 1s2, 2s2 and 2p2, right? Now what happens in this case is the 2s electrons will jump, the 2s electron will jump to the p orbital. This is the excited state of carbon. Now in this particular case, one s orbital, this one s orbital and three p orbitals, one s orbital and three p orbitals will intermix together to form a hybrid orbital known as sp3 hybrid orbital. One s orbital is intermixing with all the three p orbitals to give sp3 hybrid orbitals of equal energy and shape, identical shape. Now let's take a look at the other hybridization. Oh sorry, first let's take a look at the structure. The structure of CH4 will be like this. This is not the actual structure. This is made in 2 dimension. Let me show you. This is the shape of sp3 hybrid orbital that we can draw on a piece of paper or in 2 dimension. These are the 4 hybrid orbitals, and each hybrid orbital is of equivalent energy and shape. By shape it means the angle between the two is equal, that is 109 degrees and I think 27 minutes. And each hybrid orbital is bonded with one hydrogen atom. The shape is tetrahedral, but this is not the actual shape. This is the shape that you can draw on a 2 dimensional sheet. In reality, the actual tetrahedral shape is like this. Take a cube and put hydrogen on alternate corners. Put hydrogen on alternate carbons, alternate corners, and put the carbon atom at the center. This gives you the actual tetrahedral structure. if you can imagine it and you can use it, if you can use it for your future reference, then remember this is the actual structure of methane, that is tetrahedral structure, and the hybridization is sp3. We will talk about the hybridization and shapes of different molecules in the next video. Now the other hybridizations that you will study are sp3d, sp3d2, sp3d3, dsp3, d2sp3 and dsp2. These are the hybridization that you will study, and I will also make a video on these hybridization by using different examples of molecules that gives sp3, sp3d hybridization, sp3d2 hybridization, like that. Before we close the video, remember that hybridization is not a real concept. Hybridization is hypothetical. Hybridization is hypothetical concept. It is an imaginary concept. There is no physical significance of hybridization. We use it for our convenience. That's it. Also remember that, but it is an important concept for various molecules and structures. So just don't think of it as bad concept, but you have to use it in various examples. We will talk about those examples in the next video, and we will also discuss these hybridization that we are leaving today, right? So this will be it for today's video. Thank you very much.